And very good morning to everyone. All right, so I was a little bit confused about the pattern of the talk here. Anyway, so I had sent abstract, so thinking that it is a conference mode, but I think it is more like a workshop mode. So where we cover more of the introductory material, and so anyway, I'll keep the content same, but I'll try to go as slow as possible. So I'm happy to get questions in between, so please stop me if something is not clear. I may or may not answer, but at least we can discuss. Okay. So this is the topic I'm going to explain. So some recent explorations of nuclear spin dynamics. I'll be giving some example for unitary dynamics and something called superposition of unitary dynamics. So I'll explain what do we mean by that. And then if time permits, at the end I'll show a couple of or just one example, a couple of slides on non-unitary dynamics. Okay, so what is interesting about it? So unitary, superposition of unitary and non-unitary dynamics. So that's the topic. Okay, so as shown here, so this is the basic of nuclear magnetic resonance spectroscopy. So for students, if nothing else in the talk, so you should have this as a take-home message. So here is the magnet. So it's a very strong magnet. It is like 10 to 20 Tesla, or even stronger Tesla. The highest available nowadays in the market. If you have money, you can buy 25 Tesla magnet, and so they are very, very strong. At the same time, they are very, very homogeneous. And so previous speaker Anant talked about how homogeneous they should be. So the homogeneity we are looking for is 1 part in a billion or better than that. So 10 power minus 10 is also that is the market standard. So if there is a like 10 Tesla magnetic field, so we want a fraction of a micro Gauss. That's the field. Okay, so that's the homogeneity over the volume of the sample. Okay, so that should be the goal. I'll tell you why. So if the so now this is the sample, and that sample consists of some organic or inorganic molecules, and so this is one example, chloroform. Okay, so we usually take samples where there is no net electron magnetic moment. That means diamagnetic samples. Okay, there is no paramagnetic compound here, because we don't want to see electron spin. Okay, so why? Because we later we will see that nuclear spins have much longer memory. Okay, so if there is electron spin, then it will completely override. Electron spins are much stronger, 1000 times stronger than nuclear spins. So you will not, it will drown the signal from the nuclear spin. Okay, so we don't want to see electron spin. So we take only diamagnetic samples. So this is one example, chloroform. Okay, so it has 1 carbon, 3 chlorine and 1 hydrogen, and here is the hydrogen nucleus. So from now onwards, we don't talk about electron spins.
The size of the sample.
Yeah, right. So this is like the length is 5 centimeter, and width is 0.5 centimeter. Yeah.
You said homogeneous equipment, 1 part in billion.
Yes.
So over what range?
In this volume. In this volume, the field should not change by 1 part in a billion.
Okay, that is 5 centimeter.
Yes, yes.
Okay.
Yes, and that is achievable by using superconducting magnets, and there are additional coils here. They are called correction coils or shim coils. There are like 30-40 additional coils, and they are these days these are all programmed by machine learning, and with a single click of a button they correct the field. Okay. Okay, so now that's the nuclear spin of the hydrogen, which is proton. And we know that proton is a spin half particle, and we have spin half particle in a very, very strong magnetic field. So there is a spin magnetic field interaction, that is Zeeman interaction, and so there is a Zeeman energy gap. The parallel state will have lesser energy, so mu naught beta, mu naught b, okay, H equal to minus mu naught b, that's a Zeeman interaction. So mu naught is the magnetic moment. So m equal to plus half will have lesser energy, m equal to minus half will have higher energy. So plus half we can assign up arrow sign, and minus half we can assign down arrow sign, and so there is a energy gap. So that is the Zeeman energy gap, okay. And this energy gap, if you convert that into frequency unit, that happens to be in the radio wave, okay. So that's why we call radio frequency waves, okay, RF. Now if you apply radio wave, RF pulse, then you can see that it can absorb that electromagnetic wave and it can undergo transitions, okay. And so when it undergoes transitions, it can go to either it can directly go to excited state, or it can go to superposition states, and so on, okay. So you can very, very precisely control which state it goes to. Okay, so now suppose it creates a superposition state, it's in superposition of both up and down, okay. Now you can also label this as in terms of qubits, you can label this as 0 qubit, sorry, and 0 state of the qubit, ket 0, ket 1, and now superposition is, now it is like a superposition of 0 and 1, ket 0 plus ket 1 by root 2, okay. So it's like a Hadamard operation, okay. So you have applied Hadamard operation and you have prepared something like this, and now what happens is this corresponds to a polarization which is not along the direction of the field. So initially you can see that if you have such a system and if you have many, many particles, you don't have one chloroform molecule, you have Avogadro number of chloroform molecules, and so there is a Boltzmann distribution, right, and so there is more spins aligned parallelly to the magnetic field than the spins aligned anti-parallelly, and so there is a net magnetization, and that net magnetization can be tilted by resonant radio waves. So you have to make sure that the frequency of the radio wave matches with the energy gap, okay. So that's a resonant radio wave, and for about 10 Tesla it will be about 400 megahertz. So that's the number that you can have, okay. So we work with 400 megahertz, 500 megahertz spectrometers and so on. And what happens is when you tilt the magnetization away from this main static magnetic field is along this direction, which we call Z, and when you tilt the magnetization, you can see that it is now in the transverse plane, but it keeps on precessing due to Larmor precession, right. Every spin is precessing, Larmor precession, right. So Larmor precession takes place, and you can imagine this like a dynamo now, okay. So it is like a small magnet, tiny magnet precessing inside a Helmholtz coil, and that produces EMF, right, and that EMF is amplified, and that is read as NMR signal, okay. So that's the NMR signal, okay. So initially there is no signal because the spins are pointing along the Z direction, but they are also precessing, but that precession has a random phase, okay. So different spins will have different phases, so there is no XY component, there is no net XY component, so only Z component is there, but when you tilt it, there is a net Z magnetization which is tilted, and that now precesses under the magnetic field, and that produces a strong NMR signal, okay. So that's a all right. So now that's the summary of nuclear magnetic resonance. Yes.
Sorry,
Yeah.
question.
Yeah.
Yeah, like
Even without the NMR signal that you have shown there,
Yeah.
can it be put in a superposition state? Can it be in a superposition or no?
So here when I say superposition, we talk in the Zeeman basis,
Okay.
Okay. In this Zeeman basis, this is ket 0, ket 1.
Yes.
So superposition means there is a neither 0 nor 1, so it is a
Right.
linear combination of this.
But it's not
Yeah.
clear why you need the NMR signal for it to be in a superposition.
No, NMR signal comes out from the superposition. Okay, when you have superposition state in the Zeeman basis, NMR
Sorry,
signal
no,
can be detected.
then it is not, you said you apply a outside
Yes,
radio.
we apply radio waves.
So is it put in a superposition only by the application of the
Yes,
radio?
yes.
Why is that? Why not?
Because initially you have random phase, right? So all the
I see.
x and y components cancel. Okay,
And
so
this is going to give a bias to it and then put
Yes,
it in a...
yes,
Okay,
yes.
got it, thank you.
yeah,
See, because of Zeeman field,
huh,
and most of the spins will be in the ground state,
correct,
but because of thermal fluctuation, some of them will be in the excited state.
correct.
So what is that?
That Boltzmann distribution is there.
Yeah.
Boltzmann distribution. I'll come to that later. Yes, yes. Of course, there is also one phenomena called spin noise. So that talks about exactly what you are saying. Without RF pulse also, there is one tiny signal that comes out, that's called spin noise, and that also can be detected, but that's a different field. Okay. So we do apply RF pulse to get strong NMR signal. Okay, so now that's the more schematic picture. So here it is the sample, and it's a cryostat basically. It has multiple layers to insulate the liquid helium surrounding the superconducting coil. These are low TC superconductors. They work at 4 Kelvin. And so there is a liquid helium surrounded by liquid nitrogen and then vacuum and so on. That's why this is very expensive, and also the whole field homogeneity should be very, very high. As I said, 1 part in a billion ppb, and that's very hard to engineer such magnets. So that's why it is very expensive. One superconducting magnet of 500 megahertz resonance frequency costs about 5 crores. Okay, so now this Helmholtz coil that picks up the signal from the spins, and then that's a probe, and then there is an amplifier, and then digitized, and then it looks like this. Okay, so that is the EMF coming out from the probe, and this is called free induction decay or FID. So this has the same frequency as the Larmor precession. And now if you Fourier transform, you can see all the frequency components hidden in this signal. Okay. So now this tells us, this is the fingerprint of the molecule, and it's very convenient and very important for chemists and biologists. That's why NMR we don't have to worry, because funding comes from bio and chemistry proposals. Because this NMR center, for example, in IISER Pune has many NMR spectrometers, and most of them, they work 24 hours a day, 7 days a week, doing chemistry samples, biology samples, and so on. In between, we do get to do experiments for free. So although it is very expensive to initially set up and maintain, but they are mostly funded for other applications.
Case because you have removed
so
the
exactly.
RF field and they
Yes.
go back to the ground state.
Yes, exactly. So I'll talk a little bit about it. So that's the non-unitary part I wanted to explain. Yes, I'll come back to that. Yes, why does it decay? Yes.
So physics work is spin off. Physics work is spin off.
Physics?
So you know. Physics work that you do is
Yes. Yes, exactly. Yeah.
Here your liquid helium temperatures, sorry. So these are all microkelvin or?
Okay. So superconducting coils are in the 4 Kelvin temperature.
Okay.
Sample is at the room temperature.
Oh,
Yeah. So there is a thermal insulation here. This yellow thing is the sample, and that's at room temperature, or it can be even higher temperature. So it's in a thermostat where we can change the temperature. Yeah. But rest of the things inside, that's in liquid helium temperature. Yeah. Okay. Why this is interesting for everyone? Because nuclear spins, they are not isolated, they are inside the atom. Okay, so we are here considering the nucleus inside the atom, atomic nuclei. Okay. Now atomic nuclei, as previous speaker mentioned, so it has very precise, proton has very precise gamma and so on, and so it gives a very precise Larmor frequency at some particular field. Okay, so Larmor frequency is proportional to the field. Okay, if you fix the field, it gives you particular Larmor frequency. So omega equal to gamma times b. So now that gives some frequency. However, atomic nuclei, they are surrounded by electrons, and these electrons, they act like a shielding because they are diamagnetic, they shield the external magnetic field. Okay. So you can say now the Larmor frequency, you can see that energy gap has reduced, okay, because part of the magnetic field is shielded by the electron cloud. Okay. And so that shielding is now proportional to how much electron density that atom has. Okay. So higher the electron density, higher is the shielding. Okay. So now here it is even lesser energy gap. So you can also treat this as gamma is changing from different atom. Okay. Same proton but different atoms, you can think of this as gamma has changed. Okay. Why? Because of electron shielding, net field experienced by the spin is lesser as the electron density increases. So the Larmor frequency changes. Okay. So Larmor frequency shifts from atom to atom because difference in the electron density. Now that is very important because now although there are many protons in a given protein, every atom in that protein molecule has so many like 100,000 protons are there, 100,000 hydrogen atoms are there in some proteins. Okay. So now what happens is as you go from one atom to another, the electron density changes because of electronegativity of neighbors and so on. And so what happens is this Larmor frequency changes. So you get many resonance peaks, and all these resonance peaks are together form a very characteristic fingerprint of the protein. Okay.
People do this optical pumping of the electrons and spin polarize them.
Yeah.
So how is that spin transferred to the nuclear spins? Because they use that technique for hyperpolarizing the nuclear spins.
Yeah, right. So let's see, what you can do is, so you see there is a Maxwell-Boltzmann distribution here, which is very small now, okay, because energy gap is micro electron volt, external thermal energy is milli electron volt. Okay. So it is like the difference in the population is 1 part in 10 power 5. Okay. So if there is 1 here, this is 10 power minus 5. Okay. So that's very small difference. So 1 here and 1 minus 10 power minus 5. Okay. So it's very small. Okay. However, now what you can do is you can optically polarize. Means so suppose that there is an electron spin, there are different ways of doing that. So suppose that there is an electron spin, electron energy gaps are like 1000 times more than this. Okay. So that is also in the milli electron range in the same magnetic field. Okay. So now that is very large, and that electrons are highly polarized. Now you can do that polarization exchange. Okay. So what you can do is suppose that this has as high population as the ground state, you can exchange that with the electron polarization, which is very small.
How?
So that can be done by electron hydrogen interaction, the proton interaction, hyperfine interaction. Okay. So it is also called double resonance experiment. Okay. So you resonate hydrogen nucleus, proton nucleus, and proton spin as well as electron spin by microwave. Yes, and then exchange the population. Yes. Yeah. So that's a double resonance experiment. Now you can see that this population has reduced. Okay, in the excited state. So that means there is a lesser number of anti-parallel, more parallel spins. So there is a very high polarization. That's one way, and there are different, for example in NV center it is prepared in a different way and so on. Yeah.
Sorry, that means that the frequency should be very precise, that it is like not spread over the two,
Correct.
right?
So let me give you some number. For example, this the experiments that I am going to show, they were done in 500 megahertz. Okay, and in that 500 megahertz, we can detect 0.1 hertz. Yeah,
Okay.
yeah, 0.1 hertz. That's the line width.
Yeah.
And that is the reason why we need such homogeneous field, 1 part in a billion. Otherwise, we cannot detect that. And so there is no single atom in the molecule that we take. There are multiple atoms. Okay, and when there are multiple atoms, there is a nuclear interaction. Okay, so because they are all like a tiny magnet, so there is a magnetic moment here, they can interact. Okay, they can interact in different ways. One is called indirect spin-spin coupling or J coupling, and that J coupling is mediated through the covalent bond. So there is a covalent bond, atomic bond here, and through that atomic bond they interact. The nucleus of this hydrogen interacts with nucleus of this hydrogen through that. Okay, and so that coupling constant can vary from molecule to molecule, and that is also a fingerprint of the molecule. Okay, so all these are very important for chemists and biologists. And for us, what happens is now if you have 2 qubits, for us it's a qubit now. If you have 2 qubits, you have 4 levels. Okay, and now the resonance frequencies of these 4 levels, they are all different because of the coupling constant. Some transitions the coupling constant adds, in some transition it subtracts. So you have this splitting, and so these are split by J. Okay, so yellow corresponds to one hydrogen and blue corresponds to another hydrogen. Each one is split by the coupling constant. Okay, so now we have the spectral addressability, because now the resonances are different, the resonance positions are different because of the chemical shift, because of the different electron cloud density, and there is a coupling also between the spins. So we have both addressability due to chemical shift that we discussed earlier, as well as we have possibility of having qubit gates. Okay, so like C0 gate, control not gates. Okay. So now, so that's a good thing, because now we have all the things. We can address this hydrogen separately because that its Lorentz frequency is different, or I can address this separately because its Lorentz frequency is different, and they are coupled, and so on. So here is the example. So initially we have Z magnetization because all spins are pointing Z and precessing, but that phases are random, so what is only left is Z magnetization. And now you apply radio wave, it can tilt the magnetization. It can come from Z to X or Y, it's in the XY plane, or you can tilt it to opposite direction from Z to minus Z. That is actually population inversion. Okay, so it is very easy to do. We just have to apply radio frequency pulse for sufficiently long time, and it can take the excited state to ground state and ground state to excited state. It can tilt the magnetization, or you can apply 90-degree pulse along another direction, and so on. So these are all called local gates. Okay. So by tuning the RF wave, we can control the spin dynamics. Or we can use these spin-spin interactions, interaction between the 2 spins, and coupled with these local gates. So we can generate a fairly complicated gate. So this together forms a C0 gate. Okay, so that's the control not gate. And so together with local gate and C0 gate, we have universal quantum computation. Okay, so we can do any quantum computation, we can translate into this. Yeah.
If the sample is at room temperature, there will be quite a lot of spins in the opposite down state,
Correct,
right?
correct.
So then how do you make sure that your gates are actually working true?
Yeah, so that is one thing. It's that is really important question. So that is called the problem of purity of the quantum state. So in NMR, we say that we are doing mixed state quantum computing. So it is not pure state quantum computing. Statistical, yes, yes.
Mahesh, that's for universal gate, so there is Hadamard, there is C0,
Yeah.
and you need one more gate, T4 or T8.
Yeah. All those things can be made by combination of these.
Achha, achha.
Combination of local gates and such interactions. Yes. Okay, for example, this is one example. This is a implementation of quantum algorithm on a 12 qubit system. You can see that there are 12 qubits including this AB here, and so these are all different RF channels and they all have different frequencies. Okay, so for each nucleus, for example 9, I can address by this frequency. Okay, so it resonates only by that pulse, these pulses, because they all have different resonance frequencies because of chemical shift. Although these blue ones, they are nitrogen, gray ones are the dark gray ones are carbons and white ones are hydrogens. They are all same isotopes, but they have different resonance frequencies because of chemical shift. Depending on the chemical neighbor, their Larmor frequencies are shifted. Okay.
These molecules,
Yeah.
I would assume that you would have water molecules around it.
Yes.
Won't that interfere?
No. So that's a good thing. The way we make sure is we, instead of water, we take heavy water, D2O. And D has very far away resonance frequency. It is actually 10 times lower Larmor precision than hydrogen. Okay. So solvent we take deuterated. Yes.
What is the position of these?
So these positions are carefully tuned to
What
implement
do they represent?
such gates. Okay, so it's like C0 gates. So the positions are very important. They have to be carefully calculated. So the position is to make sure that proper interactions are realized. Okay, spin-spin interactions are
Sorry,
realized.
I'm not able to see how applying those pulses at those times will only address 9 or something.
Yeah, so because 9 for example, that has one particular Larmor frequency, so it resonates only with that particular RF wave.
Yes.
And so here we are applying that, okay,
Okay.
so that one. Okay, so we can combine all the RF waves. So basically we have
position of those blue things, what is that representing? That says time.
this one.
No, the time axis.
Time axis. So yes.
Why should
so
it be at those
you see,
time?
we are applying RF pulse,
Right.
It starts at some point and stops at some point.
Correct.
After that, then there is next pulse, and in between there is a delay, and
Yeah.
during that delay, spin-spin interactions takes place. This.
Uh-huh.
Okay, and that has to be carefully calculated. How much spin-spin interaction you need.
Okay.
Okay, and that much delay you have to give.
Okay.
Yeah,
And then apply the next pulse.
and then apply the next pulse. Yes.
And what does it do during that delay time?
Delay time, so there is a Hamiltonian, let me just check if I have written Hamiltonian. So there is a ZZ, yeah, so this evolution takes place,
I see.
yeah. ZZ interaction.
Okay.
So the addressability is not spatial, addressability is in the frequency domain. Okay, it is like all of us have cell phone and we are all immersed in this microwave, radio wave, right? But when the call comes, it comes only to your cell phone, right? Although radio waves are everywhere. Why? Because there is a selection, right? Frequency selection. Okay. Similarly here.
No,
So,
with the,
we are shining the whole sample with radio wave, but what is the frequency component that resonates? Okay, only that spin will absorb.
no,
Yeah.
that particular frequency component we are reading through NMR signal.
Correct.
But like in this example, suppose atom 9 generated particular frequency F1. So that came from 9th atom in that, because sample, in the mixture of sample. How will locate that 9th?
Yeah. So you see, when we, so the combined signal looks like this.
Yes.
Okay, it's a beat pattern. It's a superposition of all the signal. But if you Fourier transform, it will tell us all the components, which components are there. Okay, and this may be from that 9. Okay, so we have to first characterize the sample. Okay. Which spin gives where the signal.
Okay. Thank you, sir.
Yeah.
What about spin-spin interactions of different molecules?
Okay. Yeah. So we generally take samples. So there are different. I will show you some examples. generally it is liquid state and we keep the concentration very low. So the probability of two solute molecules coming closer is small. Okay,
You arrange that.
yeah, we neglect that. Yeah. If you take very high concentration, then we have to worry about intermolecular interactions. Okay. So right now we don't consider. Right.
But that doesn't interfere with your logic.
To some extent, yes, but those are second order effect. Yes. Yeah. So you can make the concentration dilute.
I have a question about that.
Yeah.
The spectrum that you showed.
Uh-huh.
So let's look at 9 again.
Yeah.
The nitrogen 9. So there are these red lines, or sorry, blue lines. In between there's a double red line. So what
No,
is
no.
that?
So sorry, this blue is not corresponding to that blue.
No. I'm looking at the row of N9, the green
Okay.
color N9. Yeah.
Yeah,
So
yeah.
there are these equi-spaced blue lines,
correct.
which I assume is the resonant frequency.
Yes.
But there's a little double red over there.
Yeah,
What does that
actually
mean?
here in this lower diagram, blue means it is pi pulse, it is spin flip 180 degree.
Okay.
Red means 90 degree.
Oh, okay,
Yeah,
okay, I see. So it evolves in time like that, is
Yes.
it? So how do you use it as a qubit? Because you need to know, you need to be able to change the value, right?
Yes.
Whenever you like, so.
So these are all pre-programmed and then we send it to the transmitter and it sends the pulses in this order.
Okay, nice.
Yeah.
Nice, thank you.
So for example, we have this 12 qubits and more recently another 12 qubits, and there is a one 18 qubit, and recently we have 38 qubits. That's the system, and I'll show one work with this. No, actually that is a so spectral crowding is one thing. As you can see that if you have many qubits, then there will be spectral crowding. Then addressability is lost. So it is like each telecom operator buys certain bandwidth, and they from that you can only get so many customers. Right, so if you want more customers, you have to have extra bandwidth. So spectral crowding for us is a main challenge. Yeah.
Limit that you can go up to?
Right now there are other limitations. Spectral crowding is one, and finding molecules and synthesizing them and getting stable molecules. If you make it even larger, it becomes unstable. So we want a system that stays for at least the duration of a PhD student, 5 years. Yeah.
No, I mean, there are lots of peptides which are quite stable.
But then there is another problem. So we want addressability, we want coupling network and all those things. Yes, you are right. Yeah. But then we tried some molecules which decomposed within months time, and that was very depressing for students. Yeah. Sorry?
This collection of qubits, is it a coherent collection?
Coherent?
This 38 qubits are not coherent.
So I'll show you. We can entangle them.
All 38 of them.
Yeah.
Ensemble quantum.
It's ensemble, yes. Ensemble.
Many of them.
Yes. Okay, so all right. So we can also think of other architectures. So here, for example, they have taken solid state NMR, where there is a crystal. So this particular crystal is called adamantane, and so you have a lattice now. You have Avogadro number of spins. Now it is not one molecule. It is like Avogadro number. It's like a crystal. Okay. So each ball here is a spin. Okay. Now question is, as he said, what is the largest coherent cluster you can get? Okay. So that means starting from one spin, how many spins can be quantum correlated with that spin? Okay. So cluster of how many spins, whether you can create GHZ state or even larger state, cat state of what size? Okay. So and then get the signal from that. So that's the question. And they found that they can do pretty well. So they can get quantum register sizes of up to about 4,899 spins. Okay. So this is another way, but this one doesn't give addressability because there is no chemical shift. They are all identical. So you can't address, for example, this qubit. Okay. So because exactly identical, they are exactly identical, unfortunately, so you can't use it for universal quantum computation. However, this is very good system for studying the physics of quantum registers. You want to study the decoherence time. Okay. So for example, in this paper they have studied decoherence rate as the size of the coupled system. You have prepared large quantum correlated systems, and you want to study how fast it undergoes decoherence. Okay. So for that it is good. So it is not good for universal quantum computation, but it is very good for studying decoherence. So that's another. So recently we are also trying to do something else with this. In fact, it turns out that we can do quantum machine learning without requiring universal quantum computation with such kind of systems. Yeah.
Okay.
Nuclear spins, yes.
I see.
Yeah.
So about maybe 4,000 what?
4,899. Yeah.
It's a large number.
Yes. Yeah. Yeah, and but we don't want to, even in this paper, they don't want to call that as 4,899 qubits because you don't have addressability. Yeah.
But because of coherence, you can do super radiance.
Yeah, you can do such experiments, but here they are just studying how fast that quantum correlations is lost. Yeah. Yeah. The rate of decoherence. How are they made?
Yeah.
Yeah.
Coherent, yeah.
Yeah, the way it is made is that these spins are interacting. Okay, they are interacting via dipole-dipole interaction, and so from that you can. So there is a double quantum Hamiltonian. Okay, so plus 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 minus minus. So that there is a double quantum Hamiltonian, and you can let that double quantum Hamiltonian evolve. So initially you apply a pi/2 pulse to bring them in the transverse direction and switch on that double quantum Hamiltonian, which is already there. Let them evolve under that. As you wait, the cluster starts building from every spin and starts getting correlated with neighbors, and that sphere of cluster that grows over time. Yeah.
And then
And then you do, okay, then what you do is you have to find out what is the size of the cluster, and there they do very clever experiment, because larger the size, faster it evolves under phase modulation. For example, if you have a Bell state, it evolves as a, if you apply interferometer, for example, if there is a phase shifter phi, it gets 2 phi, right? If you have GHZ state, it gets 3 phi. Right. So you pass it through the interferometer experiment. So it's again it's basically same Hamiltonian, and then you are undoing that, but there is a phase shift. Okay. Now how sensitive it is to the phase shift, and that tells you what is the size of the cluster. Okay. If it is phi, it is a single quantum. If it is 2 phi, it is Bell state. 3 phi, GHZ state, and they found that up to this much they could get. Yeah, the sensitivity. So they are saying that is the size of the cluster. Yeah. Yeah. Okay. So now also there is we discussed about it, why that FID is decaying. Okay. Why the signal is not staying as it is throughout. Once you put in the transverse direction, it doesn't remain there. That is because of these two effects. One is called spin lattice relaxation, and another is called spin-spin relaxation. Okay. So any non-equilibrium state tries to go back to thermal equilibrium state. Okay. And that is called spin lattice relaxation, because the spins have absorbed energy and they want to give away that energy back, and then energy goes back to the lattice, and lattice gets heated up. So now that that's a irreversible process. and so that is the spin lattice relaxation. Okay. And there is another, so that's a process which doesn't conserve energy, because once it goes to lattice it doesn't come back, and so that's a irreversible process. And there is also spin-spin relaxation. So where if you take this, if you flip this one spin, then it can affect the other. Okay, that is spin-spin interaction. Okay, so the spins are also interacting with one another via dipole-dipole interaction or via indirect dipole-dipole interaction, and they can exchange energy. This is partly reversible for up to some short time scales. There are methods like spin-echo, Horn-echo, and so on. So those are the methods. But for long term, again, it is not reversible. Again, this is also related to quantum chaos and all those things. So we lose track of the information, and for long term, this is also not reversible. So combination of these two effects lead to the decay of the signal, because ultimately spins go back to thermal equilibrium.
And how does one predict which kind of relaxation it happens? Spin lattice relaxation or spin relaxation?
Correct. And they happen at different time scales, and there are different methods for estimating T1 and T2. So spin-spin relaxation, that decays the transverse component of the magnetization, and T1 that restores the longitudinal component of the polarization. And there is a Bloch equation which describes how all these processes take place. And for example, if you want to measure only spin lattice relaxation, you don't create coherence. Okay, you change only the populations, and then see at what rate the populations are restored. Okay, so it is a pure population process, population rearrangement process, and so it doesn't involve spin-spin interaction. And for spin-spin interaction, you prepare coherence, okay, and then see at what rate it loses the coherence. Okay, so that is yeah.
Okay.
So spin lattice is also some coupling to an average
Yes.
spin of the lattice.
So basically, that is not modeled that way. The way it is modeled is that it depends on the system. In liquid state, for example, the spins, so they are inside the atom, okay, but whole molecule is doing all kinds of motion. Okay. Now, as this molecule is rotating and there are other spins, and there is a electron density, and so if electron density is perfectly homogeneous, then rotation doesn't matter. But electron density is a tensor. Okay, it is not perfectly homogeneous. Now, as the molecule rotates inside the main static magnetic field, you see the nuclear spin field fluctuates because it's a tensor, right? And so that's how the nuclear spin is coupled to the lattice.
I see.
Okay, so this is the effect. Now you can say that, okay, of course there is a there is one interaction that is closer to what you mentioned. It is called molecular angular momentum interaction, but there are other reasons for this. Yeah.
Your spin lattice interactions are much weaker, right?
Spin lattice interactions are weaker, and
compared
so
to
this
spin-
time scale is longer.
Longer.
Yes, yes. So this can be seconds, sometimes minutes, sometimes hours, sometimes days, but this is much shorter. Yeah.
But if you remove the solvent, just have a gas with your
That can have very, very long lifetimes. Yes, but signal will be less.
signal will be very
Yes, yes, yes. Correct, correct. And people do such gas NMR, but you need high pressure and so on. You need special hardware for it. Yeah. Okay, so now, using such systems, we can do, we can study physics of quantum computation, we can study physics of quantum control, because many of the techniques which are originally developed for NMR, they are applicable elsewhere, because the Hamiltonian structure is similar, so electromagnetic interactions are similar, so you can apply those methods to other technologies. So we can study quantum control, we can use it for various quantum simulations, we can study, we can simulate many condensed matter phenomena, for example, time crystals and so on. We can study quantum foundations. For example, we studied Wheeler's delayed choice experiment and so on. Okay, and we can of course contribute to NMR spectroscopy itself.
Just a basic question.
Yeah.
What unit of time it tells you, how many units you need in order to maintain coherence, in order to do some computation or something?
So,
Is there some
yeah,
basic
that's a
unit?
good question. A C0 gate, for example, usually it's a unit of C0 gate.
I see.
So
That
C0,
population
yes,
inversion.
how fast you can do control NOT gate. It's a
I
2
see.
qubit gate.
Okay.
So in units of C0 gate, if you can do 100 C0 gates,
Okay.
and then you can do really good algorithms. Yeah, and that can be done because C0 gate generally takes say 10 milliseconds, and up to 1 second coherence lost. So that is easily possible in NMR. Yeah.
I see.
Yeah.
And that length is needed to invert the population, is it?
That is pi pulse.
C0 is
C0 is 2 qubit gate.
Okay.
And the inversion that you are mentioning, that is spin flip, that is called pi pulse, 180-degree pulse.
C0, what happens in?
C0, depending on the control state, you flip. For example, if the control qubit is 0, you do identity operation on the target. If control is 1, you do spin flip on the target.
I see.
Okay, so that is control NOT gate. Yeah.
Okay.
Yeah. It is spin flip only, but it conditional to the state of the control qubit.
Got it. Yeah.
State of the source.
Yeah.
Control qubit, yeah.
Yeah. Okay, so what I wanted to talk about is some of these recent experiments in some of these. Let's see how far we can go. Yeah. Yes. So there are different ways. In some experiments we don't have to prepare any special states. We can start from thermal equilibrium, thermal states. But in some experiments we have to prepare something called pure states. And pure states means, so as she also mentioned, everything should be in the ground state, right? So then we can say that it's starting from all zero state. And that is very difficult in NMR. So what we do is something called pseudo pure state. Okay, and the pseudo pure state is like if you have all 0 kets plus some identity. So you decompose the density matrix into identity plus a pure state. So then it is called a pseudo pure state. Identity is the maximally mixed state plus a pure state. Yeah. And that is conveniently possible in NMR. And then what happens is this identity part doesn't evolve under unitary operations, neither it gives signal. And so whatever signal comes is directly from the remaining part, which is a pure state. Yeah. That's so we say that there is a isomorphism between pseudo pure state and pure states.
But it may be harmful for quantum computation.
I know it is harmful because it gives extra noise. And also it is not useful for certain quantum foundational experiments because that identity part we can't ignore. That provides loopholes and other things. Yes. Yeah. Yeah.
This quantum non-demolition measurement is also based on this such technique?
I don't think so.
Okay.
Yeah.
Okay.
Yeah. Okay, so let's start with unitary dynamics, and I'll be describing quantum battery, okay, as an example. Okay, so quantum battery is something that can store energy and release energy on demand. So that's a quantum battery. Okay, so it's a quantum system that can store energy and release energy. So now, as we can see that if we have an ensemble of spins all in the ground state, we can't extract energy. It's already in the ground state. Okay. So although it has high polarization, so they are all in the ground state. Now as you okay, so induced transitions. So now this is having lesser polarization because we have induced transitions. Some are in the excited state. Now we can create now more and more excited spins, but now at one point of time the excited population is more than the ground state population. Okay. So now at this point of time, now you can see that if it can hold this state for a long time, now whenever we want, we can let that extra spins to come down, it can emit energy, right? And so that's a quantum battery. Okay. So if it can store that state for a long time, then it's a quantum battery. So now the way we detect the population difference or how much energy it is storing is through the polarization. Just by looking, so because every state here has a particular polarization. So just by looking at the polarization, we can tell what is the state of the battery. Okay. So there is a very clear direct relationship between the polarization and the energy stored. Now here in the previous example, so that's everywhere there is only population, so there is no coherence, and so density matrix is always diagonal. Whereas now we can also see that it can exist in different coherent state, it can exist in superposition states, and we will see that quantum battery actually exploit this superposition state, and then they can have higher charging rate, higher discharging rate, and so on, okay, by exploiting the superposition states.
So to call it a battery, do you need to couple that transition to electrons, or is that to an electric current, or is that not?
That is not necessary.
Okay.
All you need is to a way of extracting energy.
That's right.
Whenever you need.
But it should ultimately result in an electron coupling to call it a battery, or is
No,
that not?
it can be electron or it can be some photons coming out.
That's also you
That's
call
all.
a battery.
Energy should come out.
All right.
Yeah.
Okay.
Okay, so one thing that we wanted to test is this. There is a so maybe there is this reference here which showed this is a theory work which showed that there is a difference between two ways of charging a quantum battery. One in which the chargers, these are chargers and they are charging the battery, okay, and chargers are giving energy to the battery, and so that's how battery is getting charged. That means more excited population is getting created. And in this configuration, this is also called parallel charging. The chargers are not interacting and battery is also not interacting, so it is called parallel charging. Okay. Now you can reconfigure the same system into this fashion where you are charging simultaneously one big battery. Okay. The total energy is same, everything is same. Okay. Total energy that is being stored is same. Only thing is now in this configuration they are all charging together, and so they are they are interacting and getting quantum correlated. In the second case, they are getting quantum correlated. So now what they showed is this charging time is much faster. In fact, the ratio varies as square root of n. The charging time, so tau 1 by tau n, so that varies as square root of n. That means this charges root n times faster than that configuration, okay, the battery charging. So that was shown theoretically, and we wanted to test this experimentally. N is number of chargers. Yeah. Yeah.
It's always coherent
Yeah.
in the second case.
Yeah.
Quantum is always coherent.
Yeah, in the second case. Yeah. So I mean it is exploiting that quantum coherence. Okay. And so they use this particular Hamiltonian in this case, and so
This looks like oversampled.
this correct. The speed up is like that. Yes. Yes, square root of n. And so we wanted to test that, and so we took these systems. As you can see that in this configuration there is a central battery and surrounded by charges, and we took similar topology systems. There is a central battery and surrounded by chargers. For example, you can take this acetonitrile. Okay, so this is a very common chemical, and we can take trimethyl phosphate, trimethylsilane, tetramethylsilane, or this, and so on. Okay, so we can change the, we can see that the spin number of charger varies from 3 9 and 12 and so on. Okay. So here it is all the way up to 30, 36. And then we observed the polarization of the central spin, and so in the previous slide I linked polarization to the energy stored, right, and we can get what is the maximum polarization, so I mean maximum inverted polarization, that's the maximum charging, and then we monitor what's the time taken for that maximum charging, and we plot the time as a function of number of spins, charging spins here, and that goes as square root of n. Okay. So this is an experimental proof that there is a advantage in the quantum case. Okay. So it exploits that quantum resource to have this faster charging. Yeah, so this is the efficiency, so this is charging efficiency, yes. Charging time is reduced, so charging efficiency is increased, gamma, yeah, yeah. That goes as square root of n. Yeah.
Just understand the star topology.
Yes,
So you have 5 spins.
yeah,
So they are the chargers.
yes,
So they are all parallel and it's coherent?
yes,
I see.
yes, yeah,
So it's like a super radiance,
yeah, I
but
guess so,
with
yeah.
2 levels.
Why can't you entangle them?
They are getting entangled. In fact, let me see if I have, yes, you see that now we plot the quantum discord, and then you see that it goes through maximum. So when it is fully charged, again it is diagonal, so there is no quantum correlation, but on the way, exactly in between, it goes through this maximum quantum correlated state. Yeah.
I'm surprised by saying you could arrange it to be coherent, but you're saying irrespective of your arrangement, it will be coherent?
So it is arranged in this special way, and then also there is this special Hamiltonian.
No, that's okay, but when I add
Yeah,
the star,
yeah.
I could put a entanglement which is incoherent,
So initially there is no entanglement.
right? But I add it.
Yes, this Hamiltonian entangles the spins, and then it leads to faster charging, and at the end of the charging again that disentangles. Yeah.
Okay, supposing I take a different Hamiltonian,
Yeah.
like instead of plus those two terms, I put a
Yeah.
negative.
Yeah.
Then what will happen?
That it may change. We have to see, because I don't know whether this is this behavior is universal across all Hamiltonians. Yeah, this is this depends on the Hamiltonian. Yes, yes, yeah. So that is the special Hamiltonian. Yeah, yeah.
Sometimes it might happen that this Hamiltonian is important.
Yeah.
Even in some computation, the creation of entanglement is not important, but performing some task is important. For that you need entangling Hamiltonian.
Yes.
So the discord is between what this?
So discord is between the central qubit and rest of the thing. So we
Okay.
measure only central qubit. Yeah. So central qubit is entangled with all the rest. Yeah.
Yeah.
Go to that star. See, essentially, see, it's like a central spin model. So what the B spin is doing is entangling the rest.
Yes.
So if you eliminate B, the star spin is coupled to itself.
Yes.
That's a way to see it.
Uh-huh.
That's one way to see it. Even though they all look independent, but since they are coupled to the same spin, they get entangled.
Yeah.
We will discuss it.
I see.
Sorry, what does it mean? You showed that the previous Hamiltonian, you said that this one.
Yeah.
What do you do in order to turn this on, or, like?
So let me see. Yeah, this is the sequence. Okay. So you see there is a local gate here, some local gates here, and then there is a spin-spin interaction between B and C. B is here and C are these. Okay. And so the effect of this whole thing is that evolution of e power minus hxy. Okay.
I see.
So that is.
So that sequence of pulses will correspond to that.
Yes, yeah. The reason is the following, okay, so without doing anything, you have just ZZ, okay, if you don't apply these local gates, okay, you have ZZ, okay. Now you have to rotate that ZZ interaction into XY interaction.
I see.
So these things are just rotating them.
Oh, got it.
So that's the,
Mahesh, just a quick clarification. So your Hamiltonian is the XY Hamiltonian between the central spin and the others?
that is the
What's the
average
connector?
realized Hamiltonian.
Huh?
Average realized Hamiltonian. The natural Hamiltonian between this and this
Yeah.
is ZZ.
Yeah.
Yeah.
Yeah, but the Hamiltonian which is
Realized.
which is making the charging
Yes.
is this XY
Correct.
integrable Hamiltonian,
Correct.
right?
Yeah.
And you said that the discord is increasing
Yes.
and then is decreasing to
Yes.
0,
Yes.
but the charging is, the energy or
Yeah. So this is the
that is
battery.
growing
Battery
monotonically.
energy is increasing like this.
So your initial state is unentangled and your final state is unentangled.
Correct.
And there is in between a maximal entanglement.
Yes.
So what exactly many-body correlations or resource you're saying?
Yes.
How is that, how am I to understand that? Because it's increasing and then it's decreasing also
Correct.
to 0.
Correct. Because finally, for the completely stored battery, everything, the entire energy is in the population. Okay. So it's a diagonal state in the basis of the density matrix, right? I mean, a diagonal state in the Zeeman basis.
Basis
Okay.
of what? Oh,
Zeeman basis.
Of only the central spin, right? You're talking
Of only central spin. Yes.
Yeah.
Yes.
So it's, you're talking about the density matrix of the central,
Central spin in Zeeman basis.
Yeah.
Yeah.
So is that necessarily unentangled from the others?
Yes. Yeah.
But then it will be a pure state, you'll have coherence.
No,
and-
it goes to the exactly opposite polarization of the initial state.
Okay.
If you start with
Yeah.
pure state, you will
Yeah.
end up with the pure state.
Okay.
Yes, yes, yes,
Yeah,
yes.
okay.
Exactly, yeah.
Yeah,
Yeah. So identity part is always there.
Yeah.
Okay, so the remaining, that pure state goes to that excited state,
Okay.
but identity part is there. Okay, so in our
Power
case.
is still increasing, right?
Sorry?
Battery power is increasing.
But battery power is increasing, that reaches maximum here.
Yes.
Yes.
When you say XY Hamiltonian, so is this, are you applying a magnetic field? I mean, what are you applying? I mean, a magnetic
So-
field, RF pulse, what are
So
you
we
applying?
apply
over here?
RF pulse and
RF
then
pulse.
RF pulses and then ZZ interaction, RF pulses, ZZ interaction and again RF pulses. Together this implements XY Hamiltonian.
Okay, so you have the original NMR field always?
Yes.
Okay.
Yes.
That is not switched off at all?
No, that is not switched.
Okay.
So apart from Dickey superradiance,
Can we think about this population inversion in multi-level system to be also equivalent to this
Yeah.
quantum,
Yes.
I mean, this kind of charging?
Yes, we can, if you can store it.
No, well, I mean, it kind of stores in for some time and then
You can call it, yes. Because if you can, the idea is like you charge, energize the system.
No, so the bottom line, what I'm saying is that is amplification somehow equivalent to this charging phenomenon here?
Amplification, see here, this is the speed up in the charging time. So charging time is faster in the case of quantum, okay. So now it is harvesting that quantum resource, and then it is charging faster. That's
So
the,
multi-particle coherence is also kind of,
sure, I mean that is another way, yes, yeah. Which one? Okay, this is a pulse field gradient, that is a experimental technical thing, that you want to measure ultimately the population, and if you don't apply this, there will be some spurious artifact from the leftover coherences. Okay, so this just cleans up all these things and measures only the populations. So this is a standard NMR way to measure population. Yeah.
Which is also a radio frequency pulse.
No, this is field gradient. It is like in MRI machine you apply field gradient. It is like that we also apply field gradient in NMR to dephase out all the transverse magnetization. Yeah. So, so that you can measure only the population. Yeah. Yeah.
So is there a way to tweak the, the frequency and the amplitude of these pulses to have a faster charging?
Still faster, you mean?
No, I mean,
faster than square root of n.
So have you, I mean, in this thing, is it already optimized or you could have still?
See, square root of n is proven to be the best you can do with this Hamiltonian.
With that Hamiltonian?
Yes.
Okay, I see.
Yeah.
But still, what algorithm it is also?
Correct. So, yeah, maybe, yeah. I think optimality for charging, I have not seen any paper. Whether it is optimal for any Hamiltonian, I don't.
Getting a feeling that.
Yeah, it looks like there is a correspondence, right? Yeah. Okay, so now whether you can extract energy, that is another thing. So you can also extract energy. For example, now in this system, the central silicon here is surrounded by 36 hydrogens. So that's the battery here. And there is another silicon here, and that we can take it as a load. Okay. So now after charging, we want to transfer the energy from this silicon to this silicon. Okay. So that is like transferring the energy, so extracting energy from the battery. Now the energy of the central silicon decreases and energy of this peripheral silicon increases, and that's what is happening here. Okay. So we charge and we extract energy. So now entire energy is now loaded onto this peripheral silicon. So this is the experimental data. So as you know, anyway, it is a unitary operation, completely unitary. So this is again another applying XY Hamiltonian between this and this now. Okay. So same XY Hamiltonian exchanges the energy. So now energy goes from central silicon to this silicon. So it's a periodic thing. This is the one period. Now question is, in between now if you put a storage time, so this is the charging time, charging process, this is the extracting process, in between there is a storage time. How long you can wait? Okay. So what is the memory of that battery? Now you can see this is log scale, and you can see that the charge that is stored decays like this, and up to about 120 seconds, 2 minutes, we could store about 50%. Okay, 50% of the battery is stored up to about 2 minutes. Okay, it's not great, but still at the proof of principle that this can act like a quantum battery. Yeah.
Earlier, that second molecule was not there. Later, you bring it close to the thing.
So we didn't turn on this part earlier. It was there, but we didn't turn on.
How do you selectively?
So we were focusing on only these.
Yeah.
Now we turn on this also.
But how do you do that? If you apply some pulses,
that,
it will go to
yes,
that also.
again similar pulses.
No, but these pulses will go to the second one also.
Yes. Now between this and this, between this and this.
No, but how is it only charging the first molecule and not the second one? I mean,
it's same molecule.
First pulse is
These
going-
are all in the same molecule. These are the 3 branches, and this is the 4th branch.
I see.
Yeah.
How is it that the charging only sees the left side and not the right side? Is it?
Charging only sees the left side. That is because this is applied on all the hydrogens. So C is all the hydrogens and B is the central bath. So I can resonate only the central silicon. These two have different resonance frequencies.
Okay.
Yeah. So they are differed by 800 hertz. Lifetime of the battery depends on temperature. Yes. 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 Room temperature. That we have not tested, but of course it depends. Yes. It can change quite a bit, like 2 minutes to 3 minutes. If I go to low temperature, it can go to 3 minutes or even 4 minutes and so on. Yeah.
And what about the fluctuation, while charging or discharging? I mean, is it a continuous flow of energy or there can be a fluctuation about the energy?
NMR is an ensemble method. So what we see is the average of over all the molecules. So there are these fluctuations. So maybe you are talking about single molecular level.
Yes.
That we don't see. Okay. So we see the average behavior. Yeah. Okay. So now, how much time do I have? 10 minutes, okay, good. So there is this concept of ergotropy. So in this quantum battery, so let me just touch upon that and then we can close. So Now there are two states, active and passive state. Anything, any state that can give energy out is called active state. Okay. Any state that cannot give energy out is called the passive state. Okay. So so passive states are defined like this. They can't do work and they are diagonal in the energy basis, and the populations are distributed such that higher the energy, lower the population. Okay. So that cannot give any energy. Okay. So for example, this higher the energy, lower the population. So from active state, this is an active state. Okay, that can give energy. Ultimately, it can go to passive state, and then onwards, no energy can be further extracted by unitary means. Of course, non-unitary means you can still extract. No unitary operation can further reduce the energy. Okay, so it can only increase the energy. It can't reduce the energy further. Okay, that's called passive state. So this is so diagonal in the energy basis. Okay, that's important. So there is no superposition. There is no coherence.
Sorry, that passive state is the Boltzmann distributed state, is it?
It can be Boltzmann distribution, okay, or it need not be Boltzmann also. As long as these two are unitarily connected, that's fine. Yeah. But this condition should hold. Okay. As the energy increases, the population should decrease.
And it should be diagonal, is it? That is
it should be diagonal in the energy basis.
I see.
Energy basis. Yeah.
That is a passive state.
That's the passive state. Yeah. So rho is this. It's diagonal in the energy basis, and Hamiltonian is this, and then passive state is defined this way. Yeah. Yeah. Okay. So this is just for one qubit example. Wherever the qubit may be initially, it has some energy, and moment it comes to this, that's it. Okay, and that's the minimum energy configuration. It can't go to any further, energy reducing state unitarily. Okay. You can rotate only up to this, and that's the minimum energy. So this is the passive state, and this is the active state. So now there are many questions. So we wanted to see how, from an arbitrary known state, how to prepare the passive state. This is very important because classically we know how to discharge a battery. Okay, so we connect a load to the two ends of the battery and it discharges, right? It can dissipate and it can, or it can do work, and then we can extract energy. But quantum battery, suppose we have a quantum battery in an unknown state. I don't know the state. How can I extract maximum energy and then bring it to passive state? And there is no efficient method for this, in fact, because this is related to finding the ground state of a unknown Hamiltonian, and that is also a hard problem, and this is also a hard problem. So given an unknown state, how to get to the ground state in the unitary way, okay, using only unitary operation. Okay, what is that unitary operation which can give us minimum energy state? Okay, so that is the.
Automatically will come to the diagonal state.
Automatically, that is non-unitary way. If you just wait for long time,
so
it's
you
a
want
non-unitary way. Yeah.
Okay.
Because non-unitary it takes long time. So we are talking about a quantum battery. On demand, we have to extract energy. So that's it. So that's the question. Okay, so these are the questions. And now this concept of ergotropy comes. Ergotropy is the difference between any active state and the passive state. Okay, so that's the ergotropy. So completely passive state, so that has zero ergotropy. And yeah.
Why don't I think of it? Connected.
So question is, will it work for an unknown state?
I have the control of the Hamiltonian here. So, and I construct a Hamiltonian whose ground state I know.
So, for example, a qubit is in unknown state, will it take it to this?
Right.
Any unknown state, because I suppose that Hamiltonian for certain time. So I think the problem is where to stop, when to stop. Even in Grover's algorithm, that's the problem. We don't know when to stop. So here, for example, you are constructing a rotation. How long will you rotate for an unknown state? So it is similar to the Grover's algorithm. Yeah. 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 So even in Grover's algorithm,
No, no.
Someone has to say how many solutions are there. Right?
Just to be perverted,
Yeah.
I construct a Hamiltonian which has only one state.
No, but someone don't know.
No, I know this, since I am the freedom to construct the Hamiltonian, I know it has only one state. It's so basically a projection of it.
Someone is prepared and you don't.
No, important thing is it's not a measurement because it has to be unitary. So now if you suppose your Hamiltonian rotates the state, suppose that it is rotating in the right direction, but you don't know where to stop.
No. See, what I'm thinking is I construct a Hamiltonian, which is almost like a projection operator going to one state. All the other states are almost zero. So I apply. It has no other choice. It keeps on rotating around that one state. Because the others are
No, if that can be done, Grover's algorithm can also be done in the same method. Yeah. So I think I mean maybe we can discuss, but I don't know whether it is. Yeah. So.
Here you obey God, because you can construct your Hamiltonian.
No, that is yes. We say that there is a universal control, but then I don't know whether there is any complication there. Yeah. So I will tell you one method. That's a iterative method later in 1 minute. So now, okay. So ergotropy and all those things. So we want to. Okay. So we want to first measure the ergotropy for various states experimentally. So as you can see that ergotropy increases, that means ergotropy is the useful energy contained in the battery. Okay. So initially as a function of charging time, ergotropy increases, reaches maximum and then decreases for all the systems. Okay. So when it is highest ergotropy, there you stop because that's the maximum extractable energy unitarily, there you can stop. And now how to reduce the energy? So for that, this is the way. So this is one of the ways. Your way may be another way to do that. So one way is you take that unknown state and then you apply certain, you measure certain things. So this is measuring this commutator. Okay. So expectation value of this commutator you have to measure. And then if you measure that, then it will tell you what should be the drive, what should be the unitary that you have to apply to reduce the energy. Okay. So this is the, this gives the amplitude of that, and then you apply that drive. So if drive is Hamiltonian HD, okay, and then what should be the strength of that? Basically it gives the angle. So any Hamiltonian you give, it gives how much angle you have to rotate in that Hamiltonian. Okay. And then it doesn't ensure that it reaches the passive state, it ensures that it goes towards that. Okay. It goes towards passive state. So you apply that and then again iterate. Okay. If you do that, then we can prove that, so this is based on this theory paper again, that in fact this is not just for quantum battery, any system can be taken to passive state, any system, not just battery, any system can be taken to ground state by iterative application of this. And so that's what we did. For example, we take different unknown states every time we reach the passive state. Okay, and this is the fidelity of the final state. So they start from different states, but they reach the same passive state within a few iterations. Now there are many interesting things in the 2-qubit case. So as they reach unknown, the passive state, there are two types of passive states and so on. I don't have time for it. Anyway, so let me just say that there are, in the case of 2 qubits, the passive state can be local passive state or global passive state. Okay. Local passive state means you are discharging qubits individually, okay, without any interaction Hamiltonian. And global passive state means you are also involving interaction Hamiltonian. Okay, that's a global passive state. Now, if you apply only local drive, okay, without involving interactions, you can't extract all the energy of the quantum battery. You can extract only so much energy, but not all the energy. If you involve interaction between the qubits, then you can extract more energy. That's what we see here. So if you interact, so this is the energy coming from quantum battery, it is not coming, and then you switch to global drive, and then it can extract more energy. And this x-axis here is the entanglement between the qubits. If the two qubits are entangled, local drive cannot extract energy. You need global drive. If the qubits are disentangled, then you can extract energy by local drive. If they are in between, then you can extract partially from local drive and partially from global drive. Now we can turn the problem around and ask whether how much energy you can extract in local drive and how much energy you can extract in the global drive. Can it tell you how much was the entanglement? Okay, and that is possible. And this difference between the local drive energy and the global drive energy is called the ergotropy gap. And it turns out that this ergotropy gap is a weakness for quantum entanglement. Okay, so let me stop at this point. Yeah, thank you.
The last thing that you mentioned, that you cannot extract energy from maybe similar to in electronics, you cannot transfer maximum power unless the impedance impedance equals to the load impedance.
But the only thing is it's
there
quantum.
something equivalent there? I'm just trying to see.
But here, you mean this, right? Yeah.
No. So I didn't quite understand that. But
Yeah.
I'm
So
saying
it is
that
like this: two qubits are entangled, and you are trying to minimize the energy by local operations. You can't, okay? Because the entanglement cannot be destroyed by local operations, right? I mean, local unitary operations. Okay, that's what is happening. So they are not, you can't extract energy from that quantum battery maximally. Yes, you can't reduce. Sorry, yeah, you can't reduce by local operations. So you can't harvest energy because energy is there in the entanglement. Okay. And by introducing interaction between the two qubits, now we can harvest energy from that state. Okay, by unitary means.
if you bring in another entangled system, couple this to another entangled system.
That is equivalent to introducing interaction between the two qubits.
So non-unitary will mean something like dissipation.
Non-unitary we are not using here. Yeah.
Yeah.
Local is operations on individual qubits. Yes, yes.
Yeah, sorry, and this regarding this, this state that you prepare and the Hamiltonian that you construct. So usually when I start from a standard unknown state somewhere in the Hilbert space and I apply this Hamiltonian, it goes to a standard steady state. At least for many body systems, I know that steady state is mostly thermal.
Non-unitary operation.
No, that's not a non-unitary, that's a unitary evolution.
From which state?
From whatever initial state that you construct. So it's just e to the power IHT times that initial state.
Okay, okay.
The final state would go to what is, a diagonal, what we call as a diagonal ensemble in the context of many body system, but that's a thermal distribution. That's a steady state. Okay. So I'm a bit curious as to why you think that by applying a Hamiltonian you could go to the ground state of that Hamiltonian. I mean,
why I think
starting from an individual state, I mean, usually, you don't go to ground state of the Hamiltonian, you go to a steady state which is thermal.
Yes, yes. Here also it is not actually ground state.
Sorry, I must have misunderstood.
It is the passive state. It is not the ground state.
Passive state is like a steady state. You cannot extract energy out of it.
It is not ground state. For example, ground state is here, but it goes to here.
I see. Okay. Sorry. Thanks for the clarification.
Any further questions?
All are hungry.
I don't see any, but thanks Mahesh for this fascinating talk, taking us to the quantum world through the NMR. And we go for lunch. At 2 we reconvene.